Ben Antieau, and he'll speak about the K theory of the integers mod the prime power.
Great. Thanks a lot. Thanks for the invitation. Nice to be here and see all of you. So this is a talk that's maybe a little bit out of the usual direction for this seminar, which is maybe about algebraic groups, but it seems like algebraic key theory is relatively close to that. So let me tell you about some joint work, which is with my collaborators, Achim, Krause, and Nikolaus, who are both at Münster. And this is really a mix of sort of algebraic key theory and some modern methods in cohomology, p-adic cohomology theories, as well as some computer calculations. So we'll see a little bit about what goes into that. So let me start with the main problem here, which is this green problem. And this goes back to the conference proceedings in 1972, where Quillen introduced higher algebraic K theory and also presented the K theory of finite fields, which we'll get to in a second. And one of the problems, the open problems that was presented in that conference, there's a collection of problems compiled by Gersten, and Swan contributed one, which just asks us to compute the K theory of rings of integers modulo some ideal. And basically that comes down to just computing rings of integers of p-adic rings of integers modulo a power of the uniformizer. So let me just fix some notation here that is going to come around for us in the rest of the talk. So we're interested in finite extensions of the p-adic rational numbers. The residue field will be K, which is FQ. It's a finite field with P to the F elements. F is called the residual degree. That's the degree of the extension of residue fields. E is the ramification index, which I haven't defined yet, but it satisfies this equation. The extension K is a degree D extension of QP, and E is D over F, if you like. And there's other ways of defining it. OK is going to be the ring of integers. It's a discrete valuation ring with some uniformizer pi. It doesn't particularly matter for us what that uniformizer is today. And so we're interested more generally in computing the K theory of these finite rings. These are finite commutative rings. Okay, so they're pretty natural from that perspective. And a related question that I'll sort of carry through with us is just what is the K theory of the ring of integers OK itself? That's a part of the story. So hopefully people can see this. Some of the technology is in the way. Oh, and you can also see this. That's kind of annoying. Okay. Sorry. I wonder if there's a way to get rid of this. Okay, that worked. On the right, there are some examples. So Z mod P to the N is the one from the title, but you also have the truncated P-typical Witt vectors of any finite field. So that's an étale extension of Z mod P to the N. You can also take, so any ring of this form OK is presented by taking the P-typical Witt vectors of the residue field. That's WK, it looks like ZP, but with some more complicated coefficients, adjoining a power series variable Z and modding out by an Eisenstein polynomial, which is just a polynomial that satisfies the Eisenstein criterion that one teaches in abstract algebra. And I say a little bit about that. A specific example is just take Z to the E minus P, and you quotient out that's what you get by adjoining an ETH power, an ETH root of P. To QP. And there's some other examples. An important one is the truncated polynomial ring over FQ. So those are all examples of rings that we're interested in putting into this question, just to get some taste of what's happening. Okay. So now let me explain a bit about what's known about this problem, if there are no please interrupt with any questions at all. I guess I'm taking K-theory to be somewhat of a given. If it's unfamiliar, you can just think of this as a sequence of abelian groups. And those abelian groups are connected to other interesting invariants of the commutative ring. Okay, so let me say a little bit about what's known. And I'll try to zoom in a little bit here. So as I mentioned earlier, Quillen computed the K-theory of the finite fields. If KR is given by this table, it's Z in degree 0, it's 0 if it's even, but not R equals 0. And otherwise it's given by this finite abelian group, Z mod Q to the I minus 1. So that's very nice. Let me just draw your attention to this important fact that all of these groups have orders prime to P, right? It's a Pth power minus 1. So the higher algebraic K groups of FQ are somehow, they have no P torsion in them at all. That's an important point. And then various work, so Quillen computed this using group homology, kind of motivated by the initial definition of higher algebraic K theory using the plus construction. And it's not an easy calculation at all. People extended, some of those ideas to some calculations of K theories of these other finite commutative rings using group homology. So something about K2 in general of OK mod pi to the n, some information about K3 and K4, and some other information about K3. And that's basically as far as was gotten with group homology techniques. Information about K2, K3, and K4. And you see that this work of Dennis and Stein was the only work that really considered the general case OK mod pi to the n. The rest of these are either in the unramified setting or in the equal characteristic setting, or really FP algebra setting. So that's what was known using sort of the classical group homology techniques that you might learn about when you first start to think about algebraic K theory. Later, important work of Hessel-Holt-Madsen gave a complete calculation of the K theory of truncated polynomial rings. And note that this K theory, there's these coefficients ZP. All that means for the purpose of this talk is that you P complete every K group. And that has the effect of excising any information that's prime to P. Okay, so you P complete the K group. They gave this table of groups. So again, it's the p-adic integers when R is 0. It's 0 in positive even degrees. And it's this complicated formula involving the big vit vectors. That it doesn't really matter what that is. Let me just emphasize that the order is this number, Q to the I times n minus 1. Here, I is this number, and n is again the power that we're quotienting by. So their technique uses what are called trace methods and topological cyclic homology, called TC. We'll get back to that in a bit. And using those methods, people proved several other results. So Brun calculated the K theory of Z mod P to the n in significantly more generality up to degree P minus 3. Which is the first sort of real breakthrough in this particular problem. You see all the previous stuff was restricted to K3 and K4. And then Engeltveit computed it in even higher degrees. So he does the unramified case up to degree 2P minus 2. And about twice as good as Brun. And then finally, Hessel-Holt and Madsen also computed the K theory of the p-adic rings of integers, the p-adic K theory of the p-adic rings of integers. And it's given by these tables. in positive odd degrees, there's a free summand, which is ZP to the degree of the field extension plus a single cyclic torsion group. And in even degrees, it's a single cyclic torsion group. These WIs are defined here. You basically, let me just paraphrase and say that the more roots of unity your field has, the bigger WI is. Okay, so this is something about the structure of sort of the p-adic part of the cyclotomic tower of K. And that's what goes into here. And so all of these are proved by trace methods. Let me mention that this calculation of Hessel-Holden-Madsen has been kind of redone recently by Martin Spears using the big advances in our understanding of cyclotomic spectra due to Thomas Nikolaus and Peter Schulze. And then it was redone again in a spirit similar to what I'm going to talk about below by Achim Matthew in some cases and by Yuri Salima in general, combining trace methods, this big advances of Nikolaus Schulze and the work of Botmorrow and Schulze on p-adic sort of motivic filtrations. So I'll say about a bit more about that in a second. And that's about what was known. That's all of what was known about this before our work. So any questions before I get on to our results? So maybe it's worth pointing out that there's almost no commutative rings for which all of the K groups are known. So Quillen gave one set of these finite fields, and using his work, people have extended that to some other cases, namely the truncated polynomial rings that we saw of Hessel-Holden-Madsen, and then these other examples, like some other singular examples, coordinate axes over perfect fields, cuspidal curves, and then double points. So like double points being something like FP adjoin XY modulo X squared XY Y squared or something like that. And that is close to an exhaustive list of all rings, all of whose K groups are known. And even knowing the orders of the groups is very difficult. Okay, so so it's a hard problem. Okay, so let me say a little bit about what we do. And so first, let me tell you some sort of reductions that are in the back of our mind as we're thinking about this problem. So first of all, Cuckoo proved in the 70s that for any finite commutative ring, the K groups are finitely generated abelian groups. Okay, so that's just a general structural fact. So the groups we're interested in are all finitely generated abelian groups. And they're torsion in positive degrees. Okay, so what we're really interested in is this sequence of torsion abelian groups. And if we look away from the residue characteristic, then we have a lot of control. Namely, Gubber rigidity tells us that the following things are all equivalent. So if I look at the K theory of OK, and I profinitely complete all of the groups, but away from P, okay, so I'll call that the Z hat prime. So it's the prime to P profinite completion. Then that satisfies a very strong rigidity property. Namely, it doesn't change when I mod out by this pi to the n, and that's because pi is a Henselian ideal inside OK because it's a Henselian DVR. Okay, so if I'm interested in prime to P information, these are the same. And that is also true when I go all the way down to FQ. And as I remarked earlier, the K theory of FQ is basically already prime to P torsion, and they're torsion abelian groups in positive degrees, which means that this is just the same as the K-theory of finite fields in positive degrees. So to sum up, if we're interested in the prime to p part of the K-theory of OK or of OK mod pi to the n, that's already computed by Quillen. So what we're really interested in is the K-theory with p-adic integers, coefficients. So the p completion of the K groups. That's where the action is for this problem. And the next main result is that K-theory spectrum is the same as a certain spectrum built out of topological cyclic homology. Okay, so to compute the K groups, we just have to compute this TC. And I remark in this parentheses that this TC doesn't really need p-adic coefficients. TC of a p-complete ring is already p-complete, and this is p-complete because it's actually p-torsion. So we don't need to worry about these coefficients anymore here. And that follows from this Dundas-Goodwillie-McCarthy theorem or from recent work of Krause and Matthew Morrow. Let me mention what's going on behind that just very briefly. The important thing about TC and the reason that it's studied is this Dundas-Goodwillie-McCarthy theorem, which says that if you have a nilpotent extension of rings, so the one we're interested in about is OK mod pi to the n to FQ, that's has a nilpotent kernel generated by pi, and pi to the n is 0, right? So what it says is that that I can look at this commutative diagram of K-theory and TCs. So these are both just some theories that are functorial and commutative rings, and there's a natural transformation from K-theory to TC. And it says that in this case of a nilpotent extension, this is actually a pullback square, which means there's some kind of Meyer-Vietoris long exact sequence when I take homotopy groups. And so that relates the K-theory of this to the K-theory of this, the TC of this, and the TC of this. But we've already remarked that in high degrees, there's no p-torsion information in the K-theory of this. And that's also true. There's no sort of p-adic higher homotopy groups for TC of FQ. And that's why we get this result that in in non-negative degrees, these two are the same, because we have this pullback square, but these two sides don't contribute any interesting p-adic information. So those are just some kind of preliminary reductions. What we've done is we've just said for prime to p information, we can reduce to the K-theory of finite fields, and for p-adic information, we can reduce to this exotic theory TC, which I haven't said too much about yet. Okay, but the point about TC is it's a little bit closer to like Hochschild homology or Theorem cohomology, differential forms, and things like that. So it's something that seems a bit more accessible. And part of this project, in some sense, is about actually making that more accessible. Okay. So, right. So now what we need to do is compute TC of this. And this is where some modern connections with prismatic cohomology come in. So in their second paper, Botmorrow and Schulze construct for a very large class of rings, the so-called quasi-symptomic rings. It doesn't really matter what that is, but OK mod pi to the n is a typical example. There's a motivic filtration on this TC. So it's a filtered spectrum, or if you like, there's an associated spectral sequence. And the associated graded pieces of this filtration are what are called the p-adic symptomic complexes. Sorry, that's these ZPIs, then shifted up into by some degree. So these are these p-adic symptomic complexes. And let me just say what they are. So what they are, it's the fiber of a map on something involving prismatic cohomology. So this prism sub R is absolute prismatic cohomology. This curly braces I is what's called a Breuer-Kissin twist. And this n more than or equal to I is what's called the Nygaard filtration. And in this setting, there's this map can minus 5 from here to here, and we take the fiber. So I'm gonna say a bit more about this in a moment. My dog really wants to go outside, so let me let her outside real quick. Okay, come on. Okay, so so upshot is that there's some spectral sequence starting with things built out of prismatic cohomology, whatever that is, some kind of mixed characteristic generalization of crystalline cohomology, and converging to TC. And that means if we can compute these complexes, then we're very happy because we can compute these complexes. Oops, what's happening? We compute these complexes. We can hope to compute this spectral sequence. That will have computed for us TC, which is the same as p-adic K theory, and then we're done. So that's the general strategy of what we do.
I mean,
so let me give them
something.
Please.
So of course, in some situations, there's a spectral sequence from motivic cohomology to K theory. So I don't know if you would just want to say, is this the same thing, or that doesn't work, or whatever?
Right. So yeah, Bert's absolutely correct. There's also this spectral sequence was sort of, I assume, was somewhat motivated by the fact that there's a motivic spectral sequence on K theory. But, the context for that spectral sequence is typically smooth schemes. And OK mod pi to the n is not smooth. So there's not a completely direct analog. What is known is in the case that you have maybe a formally smooth scheme over ZP, the map from K theory to TC does sort of preserve these filtrations in both degrees. That's a result of recent work of Akil, Matthew, and Bhargav-Bhatt. So this is some sort of version of the motivic filtration studied by Bloch and Friedlander and Suslin and company for TC instead of K theory. But it's sort of nice because it works for any kind of reasonable p-complete ring without any smoothness hypotheses or anything like that. So that's a little bit about that. Okay, let me get this door because it's basically 100 degrees here, so I don't want to leave her out there. So okay, so that's a little bit about that background. And so now the goal is really to understand ZPI of OK mod pi to the n, and that's what we do in the next theorem. So this is our main theorem. It says that we can compute this weight I symptomic cohomology of OK mod pi to the n by a specific complex. So we look at W refers to the Witt vectors of the residue field. And so it's either this 3-term complex with free modules over the Witt vectors of given rank, I times n minus 1. So that's this I and this n coming into play at that point. Now these maps, it's one subtlety because there's a Frobenius in the picture. These maps are not W linear because they involve the Frobenius. So if we expand this out and write this as a free module over ZP, then we get actually linear maps. So this is a free module of rank F times IN minus 1, so on and so forth. And the real point is we construct explicit bases so that these sin 0 and sin 1 are actual matrices. Okay, that's the theorem. Is basically that we can do that. Once you've done that, you see that this ZPI is just computed by taking the cohomology of this actual chain complex of finite rank ZP modules. Okay. So the theorem is in some sense that there is a small model like this and that we can find explicit bases for these terms so that we can express these sin 0 and sin 1 as matrices. So this first one is always injective for weight. Maybe I need to say weight I at least 1 here. Oh yeah, I said that up here. Yeah, right, I more than 0. So in positive weights, we can do this. Weight 0 is easy. That just always spits out ZP. So it's straightforward to take care of that case. So this sin 0 is injective. And that means that this complex has cohomology just in degree 1 and degree 2. And that has the effect that the spectral sequence degenerates and there are no extension problems. So what that means, in fact, if you unwind things, is that K2I minus 1 is just the degree 1 cohomology, and K2I minus 2 is the degree 2 cohomology in an appropriate weight. And that means that all of these groups are effectively computable. So in any given range for any OK mod pi to the n, one can just compute the groups. Okay, so that's the main theorem, and I can say a little bit, yeah. So let me pause for a moment, sharing here, and show you instead. Maybe what I should do. I wonder if I can do this. Yeah, let me instead show you a spreadsheet of some outputs of our computations. Let's see. Okay. Okay. So hopefully people can see this spreadsheet. And what we have here are the results of our computer calculations with a specific algorithm that we implemented in Sage to spit out these, to basically compute these matrices and then spit out the cohomology. So the columns are a given Z mod P to the K. So here, this highlighted column is Z mod 4, this is Z mod 8, this is Z mod 16, and so forth. And the rows are a given K group. Okay, so this is K3 of Z mod 4. This is K4, and so forth. The yellow boxes are groups that were already known by previous work, and the green boxes are groups that are new from our work. And we have some for p equals 3 and p equals 5 and so forth. I'll say a little bit about this. Here's some interesting rings of order 8. But let's focus on this spreadsheet. And so you can see here that K7 of Z mod 4 is Z mod 2 plus Z mod 8, 2 to the 1 plus 2 to the 3. And you can see all kinds of different sort of shapes and maybe the hazy images of some patterns. And I realized this morning that this was not completely filled in for some reason. So I had that running. Let me just show you a little bit how this looks like in practice. Right. So there's some script. This first box, I already ran part of this because it takes a little too long. There's some initialization. Here I'm saying the prime is 2. Here I'm giving a specific Eisenstein polynomial. Here we're interested here in 32 and 33, which is, if I look at 2 times I minus 1, then I see I should be 17. So I'm interested in the weight 17 symptomic cohomology. So that's I equals 7. This is the order of the uniformizer the power of the uniformizer that we're killing. And the rest of this is just some setup. So we have some things that tell us that we need to compute with p-adic precision 156. So to guarantee that we get the correct result, we need to carry around 152 adic decimals. well, decimal is the wrong word, in our computation of these two-adic numbers. And then there's some other filtration, and we have to go up to around the 34th the stage. And this box ran the main computation, which is to compute these symptomic matrices. This took about 30 or 45 minutes earlier. And now we can run this. Oops, what happened? We ran this, and this spits out the K group, the appropriate K groups. K32 is 0, so that's telling us that the even one is 0, and then this is the 33rd K group. So it's Z mod 2 plus 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 Z mod 4 plus Z mod 4 plus Z mod 8 plus Z mod 32. Okay, so that's just a little bit of it in action. I'll record those later after the talk so that they're in the spreadsheet.
Where does 156 come from? How do you know that that's enough? That accuracy.
We have a specific, we know the sizes of the matrices, and we also have an estimate of the size of the cohomology. And so using that, we know basically how much p-adic precision we need to compute the sort of elementary divisors needed in order to compute the cohomology of the complex. And then we have to do, and then there's some points in the code where we have some p-adic precision loss. So we also need to increase it even bigger to make sure that to make sure that when we lose precision, we don't lose too much and get nonsense out. And so there's just some estimate for that we pre-compute before running the algorithm. I'm sure that this can be much lower, but that's what we do for now. Any other questions? So, okay, I think that's what I wanted to say about this code. Now let's go back to the table, and we noticed an interesting sort of fact. So recall, let me go up here. This K-theory of truncated polynomial rings of Hesselholt-Madsen. Oh, now you don't see this, sorry. All of the even groups vanished. But in the case of these Z mod P to the n's, there's typically some non-zero even K groups. And in fact, this computation of Engeltveit, which was the best possible before our work, was exactly up to the first place where there was a non-zero even K group. So so for example, P equals 3, it's 0 for a while, but then these even ones are non-zero. For P equals 11, it's 0 for a long time, but then it's non-zero up in degree 2p minus 2. Okay. So we were surprised to see when we looked at these tables at P equals 2 that there's some point where they're even, but then they look like they're 0 again after some later point. So for Z mod 8, we have to go a little bit farther. For Z mod 16, we have to go a little bit farther. For Z mod 32, much farther. But in each case, there's some point where the even groups start to vanish. And this was a kind of unexpected pattern. That wasn't, I mean, there's just no particular reason to expect, and we would never have guessed it without actually producing these tables. So let me go back to the notes and state the next theorem. Right, what do I need to do? Okay, so the next theorem is that this is a general pattern. For any OK mod pi to the n, there's some weight above which the even groups vanish. And this is a bound, possibly not the best bound, but a bound that we were able to show work. So for a fixed OK mod pi to the n, if you go high enough, the even K groups all vanish. Okay, that's what this says. And this was not at all expected, but it has some striking consequences. Because we can prove that there's a relationship between the orders of the 2i minus first and 2i minus second k groups. Namely, they always satisfy this relation. The quotient is q times I times n minus 1. So, of course, if these are all 0, and so this number is 1, that means in high degrees, we actually have found the number, the order of degree 2i minus 1 algebraic k groups. And that means that kind of surprisingly, the order for a fixed OK mod pi to the n, the order of the k groups is effective. The order of all k groups is effective because you have to compute up to this degree to handle the case of some even groups. And then above this degree, you just always know that the odd groups have this order. Okay, so you've reduced the computation of all orders to a finite calculation, which is somewhat surprising. And that leads to this example here, which I think is probably the first case of a ring that's not an FP algebra, where all of the orders of all K groups are known. I mean, except in maybe trivial cases where the groups are 0 in some non-commutative situations and things like that. Right, so the answer is like, there's a single non-zero even K group, which is Z mod 2. That means K3 is a little bit bigger than it should be. It's Z mod 24, Z mod 8 times 3. So I'm including the prime to P information here. And then all of the other odd K groups have this order, 2 to the I times 2 to the I minus 1. And so that's somewhat striking. And just to give a sense of how the algorithm is running, I have a couple other examples here. So if you want to compute something pretty high, like K21 of Z mod 32, which turns out to have this enormous summand in it, Z mod 2 to the 30, then you end up with 200 digits of two-adic precision, which is really a lot. And you're computing with some power series and several variables. I'll explain this in a bit. And you have to keep track of those variables like up to 54th powers. So it's really a huge, huge calculation. But this one is doable. The next one is not. I was trying to compute K35 of Z mod 64, 349 digits of two-adic precision, 95 digits of this F precision. And that my office computer ran for more than 10 days and then I killed it. It did not complete. I'm going to try to give a sense of what the real computational bottleneck is below. So that, let me think. Okay, that's it for the results. Let me ask if there are any questions. Okay, so for the methods, I didn't pre-write it, so partly so I can kind of answer the questions that people actually have about the methods and see where it takes us. The goal is to compute these symptomic complexes. So we want to understand these a little bit theoretically. So let me just remark. So the goal here is to compute ZPI of OK mod pi to the n. And the first thing is that we can get some kind of easy information about this. So this is a piadically filtered ring. Piadically filtered ring. Okay, we can give it the filtration by piadic powers. And the associated graded, if I look at the GER star of this p-adic filtration on OK mod pi to the n, well, that's FQ adjoin Z mod Z to the n. So I'm going to call anything that uses this sort of observation crystalline degeneration. We know a lot about how to compute K-theory of FP algebras. This is not an FP algebra, but it is an FP algebra up to filtration. And that's really, it's not necessarily helpful for the final calculation, but it is helpful for getting some kind of bounds on the problem. Because it means that there's a filtration, I'll call it F star, on the symptomic complex. So somehow if you've put a filtered ring in, you get a filtered object out. And if I look at the associated graded of this filtration, this F filtration on the symptomic cohomology, then it has the same associated graded, then it's the same as the associated graded of the filtration you get on, on the symptomic cohomology of the associated graded. So FQ adjoin Z mod Z to the n. Okay, so there's a filtration on this, and we can get some information about the graded pieces of this filtration from looking at this ring. And that's very helpful because we can just compute everything that you could want about this. Okay. So let me yeah. So let me just sort of briefly summarize by saying that that using this, you can show the following sort of equivalences. Specifically, you can show that, let's see, how do I want to say this? Yeah, here we go. So first of all, you can show that in high filtration degrees, this vanishes. So you can delete everything above weight, F weight, IN minus 1. And you can also ignore weight 0, it turns out. Okay, so this is by arguing using this crystalline degeneration. You can make a sort of soft argument to get yourself into the case that you have this filtration on the complex, but you only care about it in small weights. And this is already enough to show that, to prove some things, like it's already enough to prove that ZPI of OK mod pi to the n, that the cohomology of this R, I guess, is 0 for R not equal to 1 and 2. And this is for I positive. So there's some kind of easy work to be done to say that that these symptomic complexes aren't too big, and this is already enough to know that the spectral sequence degenerates and that there are no extension problems. And you get this finite filtration aspect of things. Okay, so this crystalline degeneration is very effective for showing some sort of qualitative things about this. And now let me try to give a sense for how we actually compute this symptomic, these symptomic complexes. Okay, so I remember I said that ZPI of a ring R in general is given by this fiber. Some part of the Nygaard filtration of Roy-Kissin twisted prismatic cohomology, and then fiber of some can minus phi map, and then going to Roy-Kissin twisted absolute prismatic cohomology. Now the problem is, how do we compute these things? And if we can compute these, then we're very happy. This filtration business also extends to these, so that we can view this filtered symptomic cohomology as the fiber of some filtered versions where there's an extra additional F filtration in the picture. Okay. And that is at the end of the day going to be the source of the finiteness of the problem. Okay, that's why we're going to be able to reduce this to a finite problem. So, but so far it's still a little bit complicated, and we don't know much about this absolute prismatic cohomology. So now let me finally say something about what this is. Well. So let me say something about absolute prismatic cohomology of R. So there's a site, R prism, and it consists of diagrams of the following form. R, I'll write B bar and B, where this is B mod an ideal I. And so it's diagrams like this. And what are B and B bar? And with obvious, commutative diagrams between those, B is a so-called prism. So specifically, it's a delta ring. So that's the same as a ring. That's a ring with a lift of Frobenius. If it's p torsion free, and that's enough for our case. So I'm not going to stress too much about the difference. But yeah, I mean this delta. So if phi is the lift of Frobenius, then delta is a set theoretic operation which satisfies phi of x equals x to the p plus p delta x. And so from this, you can figure out that delta 1 is delta 0 is 0, and there's some additive formula plus some polynomial x to the p plus y to the p minus x plus y to the p divided by p. This has integer coefficients, and then some multiplication formula. So this is delta x y to the p plus x to the p delta x plus p delta x delta y. So those are the axioms that delta satisfies. This is just some kind of algebraic structure. So a prism is, first of all, a delta ring, and together with I is locally of the form D, where delta D is a unit, and then finally B should be PI complete. And let me just ignore sort of the differences between derived completeness and so on and so forth. But that's the rough idea. So prismatic cohomology is built from this site where we look at all absolute prismatic cohomology. We look at all prisms, which are just these structures, and a map from R to B bar, which is the quotient of B by this Cartier divisor. Oh yeah, I should say, yeah, D is a non-zero divisor too. And okay, that's something. We can equip this with some topology. It's common to give it sort of the, you know, sort of P completely faithfully flat topology. And we have a structure sheaf on this, which takes this, really I'm defining the opposite of a site, right? Because you should sort of take spoof to get the site. There's a structure sheaf which sends such a diagram to B. And the prismatic cohomology of R is given by the derived global sections of this site with coefficients in the structure sheaf. And this should be similar to thinking about crystalline cohomology. In that case, there R would be, you know, in that case, B would be some ring together with an ideal with divided powers, and then you'd have a map from R to that ring modulo that ideal. And that's sort of like PD thickenings of R. So this is some sort of generalization of crystalline cohomology. Now, the problem is, right, okay. So this is good. The problem is there's no particular way to directly compute this absolute prismatic cohomology. So instead, what one does is uses some descent to a relative prismatic cohomology. Okay, so that's absolute. Let me talk about relative. So if now A is itself a prism, so these notions were defined by Bott and Schulze, generalizing sort of and clarifying work of Bott, Morrell, and Schulze. So A should be a prism, and now you're going to look at the following site and just do the same thing. Now you do A, R, and you look at maps of prisms like this. You look at commutative diagrams. So here, the only difference is we're fixing a base prism, and then all of our objects here should be prisms over A. And again, there's a structure sheaf, O prism, which sends such a diagram to B, and then this is the cohomology of that. And so what we really do is we don't really quite compute the prismatic cohomology of R directly. Instead, what we're going to do is what we call Breuil-Kissen descent. And we want to compute prism R, well, specifically OK mod pi to the n. Well, okay, let me just let R be OK mod pi to the n. We want to compute prism R by descent from prism R over some specific prism where we have more control. So let me call that prism A0. A0 is going to be the Witt vectors of the residue field of R adjoin Z. So this is a so-called Breuil-Kissen prism. I need to make this a prism. So what do I need to do? I need to make this into a delta ring first. So on the Witt vectors, I have the Witt vector Frobenius, and that just means I have to tell you what Frobenius of Z is. So Frobenius of Z is Z to the P, or equivalently, delta Z is 0. So that makes this into a delta ring. And now we need to make it into a prism. And the prism I, in this case, is the ideal generated by an Eisenstein polynomial where WK adjoins Z modulo E of Z is isomorphic to OK. So I present my ring of integers OK as a quotient of an Eisenstein polynomial. And it turns out that this is distinguished. Exercise, check this for E of Z equals Z minus P. That would be the case. That would be the case, right? you know, if I did this, if I wanted to get z mod p to the n, here I would be taking this modulo z minus p, and that's zp. Okay. So this is the case that we care about. And now the nice, right. So the goal, the basic idea is that we're going to try to compute this by first computing this and sort of descending along this map. And the diagram that does that is the following. I look at a cosimplicial diagram of sort of Breuil-Kissen prisms, where this is WK adjoin Z. This is WK adjoin two variables, Z0, Z1, Z2, or Z0, Z1. This is K, the vid vectors adjoin three variables, Z0, Z1, Z2. These maps are the obvious maps between them. And this is some kind of cosimplicial delta ring. It's not a cosimplicial prism, right? Because, for example, delta 0 of E of Z is E of Z0. On the other hand, delta 1 of EZ is EZ1. And these are just not, these don't generate the same ideal inside here. Okay, so there are two, broadly speaking, there are two or three ideas to sort of finish the argument. So first, we introduce a new theory of prismatic cohomology relative to delta rings. And it's so stupid. It's a very simple idea. It's just in this original diagram where you look at this site. Now, you just don't require A to be a prism. You require this to be a delta ring and this to be a delta ring map. But if the site still makes sense, B and B bar are still prisms. And you can define this prism R over A. Now here, all of these maps map down to OK mod pi to the n by sending each of Zi's maps to pi. And so what we prove is that there's a natural map from the absolute prismatic cohomology to the tote of this prismatic cohomology of R relative to this cosimplicial delta ring, and that this map is an equivalence. And that means that we can do descent, we can get information by descending. So that's point one. Point two, that doesn't necessarily help us compute anything. Point two is that these are also filtered. So the A dots are really filtered delta rings in a very specific sense. But let me just note that what I mean is that these have Z-adic filtrations where I filter by powers of Z, the maximal ideal, which is generated by the Z's. And delta of that ideal, the Z-adic ideal, is contained in Fi times P of that. And that's our definition of a filtered delta ring, when a filtered ring has a delta ring structure and they're compatible. And that turns out to have a lot of important consequences, but in particular, it means that we can compute like some kind of filtered slice as tote of the sort of corresponding filtered slices here. Finally, let me just say one more brief word and then I'll be done. You still have to do some actual calculation. This is just giving you some facts. And so what is the main thing that makes this work? Well, the main thing is the theory of prismatic envelopes. And so let me just say that it just turns out that this prismatic cohomology of R, let me just do over A0. So because, right, this just turns out to be a specific construction that lives purely in algebra over A0. So it's the sort of P E of Z completion of this prismatic envelope. And what is this? Well, this is a construction in free delta rings. So I take A0 and I freely adjoin a delta ring generator X. And then I mod out by a specific delta ideal, namely that Z to the N should be equal to X times E of Z. This is just saying that Z to the N becomes divisible by E of Z in this ring. Okay. And so this A0X, this is a polynomial ring on symbols X, delta 1X, delta 2X, dot, dot, dot. And then I'm modding out by this delta ring, which I get by I take this generator and then I just apply all delta iterates to that generator. That turns out to give me a regular sequence. And then what does that have to do with computations? Well, let me just try to convince you that this is helpful. So Z to the N, the weight of Z to the N is N. And so since these are filtered delta rings, the weight of delta, so that implies that the weight of this X has to be equal to N in order for this to be true. And that means that the weight of delta to the I of X has to be equal to P to the I times N. So the point is that if we only care about a finite weight, most of these classes are just above that weight, which means we can reduce to finitely many and try to figure out a basis for all of the different terms involved. That gives us a computation of the sort of p-adic symptomic cohomology over A0, and then we can do it over A1 and fit it into some cosimplicial diagram, and compute it that way. Okay, so that's a sketch of the argument. I'll stop there.
Thank you. Are there any questions?
I guess it wasn't sort of totally obvious to me at the end how you got it down to free modules of ranks relatively small and computable. In some sense, here it looks like you've got these kind of infinite complexes, and yeah, you kind of approximate them up to a certain amount. But why does it actually come down to literally finally generated modules?
Right, good. Okay, so thanks. So I guess the first thing is that this, just like we can do this kind of Breuil-Kissing descent to compute this prismatic cohomology, we can also do it to compute the symptomic cohomology. There's some relative symptomic complexes, and the thing is, by this sort of argument using crystalline degeneration, so it just turns out that each of these complexes turns out to have cohomology just in degree 1. That's a check. And then this, we know from this crystalline degeneration that it has cohomology only in degrees 1 and 2. And that just means that we don't care about too much of this complex. That means we really just care about what happens in the first 3 terms of this. because outside of that, it has to be exact from the spectral sequence, because this somehow from the sort of tote spectral sequence, these are all living in cohomological degree 1. And so this, the cohomology of this is just literally the cohomology of the associated cochain complex off by a degree. And so then that reduces us, first of all, to these first two calculations. But now I guess I'm saying is that, yes, this looks like a big ring, but we only, these delta IX, the weights go off to infinity, so we can just ignore them for our purposes. So there end up, for a given one of these, there end up being only finitely many of these weights of these monomials that we have to worry about. And so then you can just sort of figure out what all of the terms computing these complexes look like. And maybe it's worth remarking that it's kind of lucky. I'm not sure that's the right word, but it just turns out that despite this complication, like various monomials actually do form a ZP linearly independent basis of the terms. Like there don't end up being kind of weird cross terms. Otherwise, it would be a lot harder, I think. Hopefully that says something.
So Ben, getting back to the K groups of Z mod 4.
Yeah.
You said, for example, you know all their orders. Yeah. But you don't know the actual group structure of them. And that one you just computed for us on the fly this morning, I mean, it had all kinds of crazy, summands. So, but can you get a sense of like the Z2 rank of this group? I mean, can you just take this whole computation and just tensor it with Z2 and then just actually do linear algebra, over F2 and actually just know the F2 rank of this group? Or is it not that easy?
Currently, we don't know. It's a great question. I think we can, the next step once we finish writing all this down is to mine these tables for more things to try to prove, for sure. But at the moment, we don't have any particular extra guesses. I'm sure there are additional patterns. The end goal is to get a complete description, based on the computer calculations. But, some funny things happen, like the number of terms grows and shrinks, and it's not completely clear to me what the answer is going to end up being. But I guess part of it is also we haven't been able to generate big enough tables with our current code. So I think there are some guesses we have, but we don't quite know what happens. So once we finish maybe a better version of this code, we can try to do a bit more.
Any other questions? Well, if there are no other questions, let's thank the speaker again.
Okay, thank you.
We'll